Hello, welcome again. We are covering the topic Axial Flow Compressor for Civil Services Mains IFS at GATE Aerospace exam, and we are covering the topic Elementary Theory of Axial Flow Compressor. And in this, first we have studied this TS diagram, and this is referred to this diagram. This is your stage of the compressor, one corresponding to inlet of compressor, two corresponding to inlet of rotor also, and two corresponding to outlet of rotor or inlet of stator, and three corresponding to outlet of stator. And this diagram we have studied. One is this is your empty condition, and this is the final condition, and these are the stagnation condition at the exit, and these are the stagnation condition at the exit of rotor, and these are the static condition at the exit of rotor. Okay, and these are the stagnation condition at the inlet of rotor. And from this diagram we studied that the work done is your energy work input is your energy increase in rotor, that is mc2 t0 2 minus t0 1, because there is no energy imparted in the stator. So now we will study this velocity triangles of the compressor. So as there are two stages, first is your rotor and second is your stator. Suppose the air enters the rotor blade at a velocity c1, making an angle alpha 1. So this alpha is your alpha 1 at the entry. Okay, and this c1 has two components. This alpha 1 angle is with axial direction. It has two components, that is your ca1 axial velocity, and this is your ball component. This is cw1, this is your ca1. And now we can take the mean diameter of the compressor. Mean diameter means, or mean diameter of the rotor. Here this is your axis force, and this is the tip, and this is the root, and we take this mean or mean radical mean diameter and find speed here. So that speed is v. So we are taking this v. Okay. So now this is C1, this is CA1, this is CW1. Now if we draw U here, then this will represent relative velocity in one direction, that will be U minus CW1, and this is your axial velocity. Okay. So if we find the resultant of these two, U minus CW1 and CA1, then resultant is V1. So V1 is resultant relative velocity at inlet, which is making an angle beta 1 at the inlet of rotor or runner. Okay. So now absolute velocity at the exit of the rotor is your C2, which is making an angle alpha 2, and the relative velocity at the exit of the rotor is your V2, which is making an angle beta 2 with axial velocity, and this angle is determined by the blade angle. Okay. So we know this blade angle, and assuming that CA1 remains same as that of CA2, or axial component of velocity remains same throughout the compressor, so CA1 is equal to CA2. Okay. So if we know this CA2 and if we know this beta 2, we can draw this B2, and U is same, so then we can draw this U. Okay. After getting this point, we can draw this C2, and then we can find out angle alpha 2. So C2 is absolute velocity at the exit of rotor, and alpha 2 is the angle at which it is making with axial direction or leaving the axial direction, and V2 is relative velocity. Okay. So these are the velocities. Now add this velocity, air enters the stator and its velocity is reduced. Okay, its velocity is reduced because of some diffusion process. So C3 is less than C2. C3 is uh, the velocity of air at which it is leaving the stator, and alpha 3 is the angle at which it is leaving the stator. C3 and alpha 3 are equal to C1 and alpha 1 because it has to enter in the next stage. The air has to enter in the next stage, so it will enter in the next stage as in the same way as it is entering in the first stage. Okay. So these are the velocity component. So now I will read out these things. First point, the velocity vectors and the associated velocity diagram for a typical stage are shown in figure. The air approaches the rotor with a velocity c1 at an angle alpha 1 from the axial direction. So this is c1 and alpha 1. Analysis has been done at mean height of the blade where the peripheral speed is v, assuming flow occurs in a tangential plane at the main radius. Next point, we are taking mean radius for calculating this. The next point, combining C1 vectorially with the blade speed u gives velocity relative to blade v1 at an angle beta 1 from the axial direction. So if we combine this C1 with u, we will find out v1 and beta 1. v1 is the relative velocity and beta 1 is its direction. Next point, after passing through rotor which increases the absolute velocity of air, the fluid leaves the rotor with a relative velocity v2 at an angle beta 2 determined by the rotor blade outlet angle. So if after passing through rotor, it will leave the rotor at a relative velocity of v2 with and at an angle beta 2 with axial direction, which is determined by the blade angle. So now we know this beta 2 and know this ca2. ca2 is equal to ca1, and then we can find out v2. Assuming that the design is such that the axial velocity ca is kept constant, ca1 is equal to ca2. The value of v2 can be obtained and outlet velocity triangle constructed by combining v2 and u vectorially to give c2 and alpha 2. So now we know the value of ca2 and ca1 because we are assuming that these remain same, and this beta 2 is known, so we can find out v2, and we know this u also. So after drawing this and then drawing this and then drawing this u, we can find out this point, and then joining this point with this point, initial point, will give c2 as this angle alpha 2. From that cw2 and c2 can be determined. The air leaving the rotor at alpha 2 then passes to stator where it is diffused to a velocity c3 at angle alpha 3. Typically the design is such that c3 is equal to c1 and alpha 3 is equal to alpha 1, so that air is prepared for entry to another smaller stage. So here this is your c2. Okay. Now after knowing the c2, this air enters the stator, and we know this alpha 2, and it leaves the stator at a velocity c3 which is less than c2 and at an angle alpha 3 which is same as this thing. Okay. So c1 is equal to c3 and alpha 3 is equal to alpha 1. Okay. So this is the these